generous introduction. Hopefully I haven't scared too many people away by implying that the talk today is going to be about astrostatistics. I think it's quite fun. I'm going to try to make it fun for you. We'll see what we can do. Particularly with an audience of this size, I'm very happy to have questions and interruptions. So just raise your hand, shout out, or whatever, and I'm happy to try to field whatever your question might be. I guess the thesis of my talk today is that almost always the majority of the astrophysical return that you get from some set of observations comes from the analysis of populations of things, not individual sources. Okay. There are classic counterexamples, the Hulse-Taylor pulsar. It's one thing, fantastic resource. Okay. But in general, when we're doing astrophysics, we're doing it with multiple sources, and we're interested in the properties of a population as a whole, not collecting individual items. Okay? And my plan today is to walk you through a number of past population analyses that I have been involved in. Conveniently, the ordering here is chronological from black holes and X-ray binaries, which I did early in my postdoc. Formation mechanisms for these unusual planets called hot Jupiters, which I did a little later in my postdoc. Earth-like exoplanets, which I did at University of Birmingham when I first arrived, and then we're going to wind up at LIGO, which I've been doing through this whole period. Each step here is going to add a little bit of extra astrostatistical complication. And then at the end of the talk, I'm going to try to convince you that by jamming all of these astrostatistical methods together in the future of LIGO, which we all know is going to be so bright you're going to need to wear sunglasses, okay? Jamming all of these things together, we're going to get maximum scientific return out of light. Okay. That's the plan. If you ask me a lot of questions, we may never get there, but that's what I'm going to try to do. So let's get started. Okay, so first, black holes and X-ray binaries. So this section of the talk is about the best electromagnetic constraints we have on stellar mass black holes. And looking forward to the end of the talk with LIGO, stellar mass black holes are obviously a major population target with LIGO. And therefore, this is a sort of sneak preview of what we tried to do when we couldn't observe any gravitational waves. And that hopefully in the future, we'll be able to do so much better. Okay? All right, so for the purposes of this section, I'm going to mostly be talking about the mass distribution of stellar mass black holes. All right? And the way that we know about these things is they live in low mass X-ray binaries. Low mass here doesn't really refer to the black hole, it refers to the companion star, which is a low mass main sequence star. And this is an artist's cartoon. The black hole's down here. Its companion is close enough that it's overfilling its Roche lobe. The black hole is stripping material tidally off the star. It spirals around the drain, so to speak, forms an accretion disk that's hot. There's the X-rays. And maybe some jets. So there's sometimes radio observations of these systems as well. And we find them primarily by looking at the X-rays, and then we characterize them by looking at the optical at the companion star. And in particular, to characterize the mass of the system, we use what's called the mass function. For people who aren't astronomers, my apologies, there's about 8 different things that are called mass functions. It's a common name, and I'm even going to slip up and call a couple different things mass functions. But in this case, the mass function involves a quantity f, which I'll tell you about in a moment. It's full of things that are easy to measure. And then this function of the mass ratio of the system and the inclination. And if you look at these terms that are not f, this one is always bigger than 1. This one in the denominator is always smaller than 1. And so the mass that you get out of this is an upper limit on the mass of the system. So f here is the so-called mass function, and it's full of 2 easy-to-measure quantities. The period of the orbit, you get that. You can look at the optical modulation. You can look at the spectral modulation. That's easy to measure. Slightly harder is the velocity semi-amplitude. This is the speed of the orbit of the companion. You can get that spectroscopically. You put a spectrograph on it. You watch the redshift. So we know f quite well. That doesn't mean we know mass as well, but it means we're getting started. The other quantities in the mass function are much harder to measure. Because these are low mass X-ray binaries, ignore the mass ratio for a second. The black hole is almost always the heavier thing here. So this Q is a small quantity. So 1 plus a small quantity squared, but it's not here. But the inclination can influence our mass measurement pretty dramatically. And the inclination comes from, the measurement of the inclination comes from ellipsoidal variation. So down here I've shown some sample light curves of one system, AO620. It's one of the best characterized low mass X-ray binaries. And you can see that there's a modulation in the light curve. Where that's coming from is, if we refer to this cartoon up here, the cartoon picture, because the companion star is tidally distorted, its temperature is not uniform across its surface. And depending on your viewing angle, if you're looking top down, you always see the same face of the star as it orbits. There's no brightness change. If you're looking edge on, then sometimes you see this point where the material is flowing through the Lagrange point, and sometimes you see the backside, and they have different temperatures, and therefore different brightnesses, and you get these variations. So the way you measure the inclination is to ask, what is the fractional variation compared to the brightness? Okay, if that's big, yeah.
Okay, so that was a nice explanation. But looking at the bottom curve,
Uh-huh.
you should see a double modulation.
Yeah, so it's bigger here and it's
Well,
asymmetric.
No, go to the next sheet. Yeah, there.
Yeah, so this is lower than this. Yeah, and that's higher and that's lower. So there's all kinds of weird things going on. I believe that this actually might be due to this hotspot that's doing something weird as you're orbiting. So you see both these asymmetric modulations, you see periodic or aperiodic trend drifts. You see momentary flashes where there'll be a sudden brightness excursion. And all of that has to do with the really complicated astrophysics that's going on in this accretion disk as things, ionization states of iron in the disk and all kinds of weird, and in fact, that leads to a lot of systematic uncertainty. We lump all those things in the context of what's called non-stellar light. Okay? It doesn't come from here, it comes from here. And because the inclination measurement is a relative one, this change relative to the level, as you add non-stellar light, you systematically mismeasure the inclination because you know how to do it. Okay, so Jerry Oros is the world's expert in this and writes codes that model the temperature distribution on the surface and put hot spots in the disk, and it gets quite complicated. But that leads to a large systematic uncertainty. And in fact, I'll tell you about a paper I was involved in with respect to that in a minute. But first, let's just pretend that we can measure inclination perfectly. We'll take the values in the literature at face value, their uncertainties, and so on. This is what you get for the 15 low-mass X-ray binary systems if you propagate the uncertainty in the inclination and mass ratio into the measurement of the mass. So the first thing you see is for some of the systems, we have a pretty good idea of their mass. For others, we don't. Yeah, John.
Well, didn't you start by telling us that this mass measurement is actually some kind of limit?
Yes.
So how do you change it from a limit to, I would think that would be a big uncertainty, that the number you're calculating.
Yeah, so we know F, the point is that we know F perfectly. And we know whether these quantities are smaller or bigger than 1. But we aren't very certain, particularly about the inclination. So this can vary. The inclination might be, say, 60 to 80 degrees. So we know what that translates to in a range of denominators here.
Oh, I see. So to the extent that you can measure I and Q, it's not, it's actually a measurement.
That's right, it is actually a measurement. But even if you can't measure I and Q, you still can. So, AO620 is one of the best characterized. It's about 6 masses. GRS 1915 is terrible. It's a little mini quasar. It's interesting for a lot of other reasons. And everything else is somewhere in between. Some of them have long tails because of the way the inclination measurement works out. So my point in showing you all of this is not to go into the details of all these distributions, but to say what we have here is a situation where each individual mass measurement is uncertain, and uncertain in sometimes weird, that is heavy-tailed ways. LIGO folks, that should sound familiar. Okay? What we would like to do with this is understand what is the mass distribution, the mass function, see, I'm not another mass function, the mass distribution of stellar mass black holes from these data. Yeah, Adam?
Two quick questions. One is, I'm sure there's going to be a difference between the mass distribution of isolated black holes and ones of others.
Yes.
And second, how many of these are extragalactic?
Actually, all of these sources, I believe, are galactic.
But there are one or two.
There are high mass X-ray binaries that are extragalactic. Yeah, IC10X1, for example. Remember, high mass here refers to the companion. That companion star is like 40 solar masses or something. I don't remember the exact value.
Are there any LMXBs extragalactic?
I don't believe we have any. Okay. Yeah, not only are the mass function of isolated black holes going to be different than this, the mass function of black holes in binaries are going to be different to this because of selection effects. Right? If we see the LMXBs, we can see that they're special. They have disks, they're radiating. Okay. So I'm not addressing that at the moment. We'll come to selection effects a little later. All right, so a thing that might occur to you is to take the histogram of the samples and the mass of each of those systems and just mush them all together. Okay, that's what's done here. And as you guess from the red X, you shouldn't do that. Okay, but that's the black curve here. And what you should do is a thing that sounds really boring. It's called hierarchical modeling. Whoever named it just didn't have any flair. David Hogg and Joe Bovee and Sam Groves are much cleverer. They call it extreme deconvolution, which sounds a lot sexier. But really, the problem is, the reason that you shouldn't do this, and the reason for this name, is that the distribution of all of the masses smushed together is a convolution of the spread of the population and the measurement errors that you have for each mass. So if the population were, say, a delta function somewhere, mushing all the samples together will never give you a delta function because the intrinsic delta function has been convolved with your measurement uncertainty. The right thing to do is to build a model of the population distribution and use that as a prior. That's your prior guess as to what each individual mass is, and then model the individual measurements in a second layer of analysis. That's why this is hierarchical. There's a population layer and there's an okay. When you do that, you find, and I have to apologize, this was when I was a young postdoc and I was very enthusiastic, and so we threw, 10 different models for the population distribution at this thing. We threw a model where the population followed a power law with an unknown exponent. Population turned on and decayed in an exponential way. Population was a Gaussian. We went through a bunch of different models. And then, though, to excuse that extravagance, we model selected them. So the best fitting model was actually a power law. Second best fitting was an exponential decay. Turn on minimum mass. Okay, so just focus on that. So the shape of the distribution that we inferred turns on here somewhere in the neighborhood of 5 or 6 solar masses, peaks around 7 or 8, and then dies. Thus confirming. Charles Bailey, one of my collaborators here, has a famous statement: all black holes are 7 solar masses. One of the things we wanted to get out of this analysis is what is the minimum black hole mass? Okay, we have some idea what the maximum neutron star mass is. It's at least less than 3 solar masses. The biggest one we've seen is about 2.1, somewhere in that range. And the question is, are black holes in a continuum with neutron stars or not? We know the stars are in a continuum from, a fraction of a solar mass all the way up to 100 solar masses or so. Are there remnants in a continuum? Well, the answer from this analysis was no, they're not. Okay? If you look at just the best fitting model, this is our uncertainty about what the minimum mass of a black hole is. And there's kind of a tail down here towards 2, but at 90% credibility, we're pretty sure that the minimum mass for a black hole is about 4.2 solar masses. Okay? The absolute heaviest you can have a neutron star is somewhere here. So there's a mass gap in this analysis. Okay? The mass gap. So the minimum mass, we think, may be telling us something about the way instabilities form in supernova. Okay, so I'm not going to go through the details, but if you read this paper by Chris Belchinski and Chris Fryer and Vicky Calhera, Dan Holt, some other people, they argue that you get a mass gap exactly when the onset of the instability in the supernova explosion is rapid. And when the onset of the instability is delayed, you don't get a mass gap, you get a continuum. So if there is a mass gap, then the onset of the instability in supernova is prolonged. Okay, great. So there's a mass gap. Great, we learned something about supernova, but
Why that follow?
all right, let me see if I can explain why that follows. So if the onset of the instability is prompt, when supernova actually explode, that is when the instability really gets roaring along, and then the energy injection from neutrinos, pumps things up enough that it actually has a breakout of the shock. When they actually explode, there has not been very much fallback onto the remnant, and they make neutron stars. On the other hand, some fail. Okay, the instability sets in, but for whatever reason, neutrino heating, the magic of nuclear astrophysics, I don't know, okay, means that there's not enough energy deposition in the shock to make it go, and so it falls back. And those form heavy black holes because all the matter basically falls back on, and so it gives you a gap. If the onset of the instability is longer, you can have successful supernova explosions where nonetheless enough matter has accreted back onto the remnant to make a 3.5 4 solar mass black hole. Okay, that's the cartoon picture, and I should, I'm not a supernova expert, but it sounded reasonable to me. Maybe you can ask a real supernova expert to see if that's actually correct. But in any case, the point is, by doing this population analysis, but in a subsequent paper with basically the same authors, here we go. Laura Kreitner was an undergrad then at Yale. She's now a grad student at Chicago, and on the rise. She's really great. Charles Balin and Vicki, who was my postdoc mentor at the time. We used 30 years of monitoring of AO620 to estimate a way to predict the non-stellar light fraction as a function of how flickery the optical observations are. Flickery is associated with accretion disk emission, and therefore the more flickery, the more non-stellar light. We made up a simple fitting formula that worked for AO620 and stuck it in to the inclination measurements of the rest of these systems and discovered that they were systematically off. So if the fitting formula from AO620 generalizes to predict the non-stellar light in the other systems, then the inclination measurements are systematically off in such a way as to move systems out of the mass gap. And if you correct for that systematic uncertainty, you move them into the mass gap. So these blue curves are basically what you get if you take the inclination measurements at face value. For the minimum mass, this is what I showed you before. You can see it, it's probably around 5 or 6, but probably, or definitely above 4. These red and green curves are what you get if you make the correction, the systematic correction, and you see the minimum mass moves right down here in the neutron star territory. Is the correction appropriate? I don't know. Okay. It's certainly sensible, but we really have no way to tell because, this is a bright system. We looked at it for 30 years. We're trying our best to estimate the systematics in this system. We have no hope of measuring this in any of these other systems. So this is the best we can get for the foreseeable future with electromagnetic measurements on the mass distribution of black holes. If only we had a way to directly measure the mass of black holes without any of these pesky electromagnetic systematic effects. That would really be something. Okay. All right, so I should say, in this we learned about hierarchical analysis. When you're doing a population, you want to build an overall population model, use that as a prior, and then fit each system in that context to extract the information. You don't want to just mush all the systems together.
Well, can I ask about that? You
Yeah.
describe your population as a prior, but as part of this process, are you also allowing the parameters of that model to, are you also fitting the model?
Yeah, so one man's prior is another man's likelihood. There's a prior on the parameters of the population. Then there's a likelihood term for the population for each source. That's a prior for the observation likelihood of each source. So it's all chained together in a fully Bayesian way, because that's what we do. Does that make sense? Yeah. Cool. All right. So All right. Now I want to switch gears entirely, much lower mass scale. Let's talk about hot Jupiter formation mechanisms. All right, so this picture is actually a few years old, but it doesn't matter much for hot Jupiters. So this is from exoplanets.org a few years ago. It's a plot of the known exoplanets at this time with an orbital period in days on this axis, and mass, well, okay, minimum mass on this axis in Jupiter masses. So this is Jupiter, our Jupiter is somewhere over here. And you can see that over here, under 10 days, there's this population of Jupiter mass things that are well inside Mercury's orbit. And what the hell is that? These are weird planets. And in fact, if you study planet formation, you would say there's no way to form a Jupiter here. You have to form Jupiters out here, and you have to bring these in somehow. Okay, so the interesting question is how? How do you get a Jupiter from 5 AU, 6 AU inside Earth? Well, there's another clue. This is another plot from about the same time. Orbital period on this axis, eccentricity on this axis. And if you squint, you can see there's a nice curve of sort of the maximum eccentricity as a function of orbital period. And for people who study tidal interactions, the fact that there is this curve is a smoking gun that tides are important. If you try to make planets' orbits eccentric, bring them in close to their host star, the star raises tides on the planet, and that dissipates energy. And it also spins the planet out, which changes the angular momentum in the orbit, and it circularizes. And this curve, this upper curve here, matches quite well the expectations for eccentric planets that are migrating and circularizing. So whatever picture we have for hot Jupiters, it better involve tides. There's one more clue. We look at hot Jupiters and we see that some of them are orbiting backwards. The way we do that is through a measurement called the Rossiter-McLaughlin measurement. This is a schematic, well, it's an actual plot of that measurement. The vertical axis here is the radial velocity of the host star, measured with a spectrograph in the way that people do radial velocity measurements. And this is a stretch of that radial velocity measurement right at the transit of the planet. So when the planet is between you and the star, it's tugging on the star, and there should be an acceleration towards you. That is towards negative radial velocity. That's the linear trend that you see here, that acceleration. But there's a wobble. Now, naively, you'd think, wow, the star jerked around. But obviously, that's not what happens. Stars are heavy. What really happened is the star is spinning. And because it's spinning, it's got a side that's blue to you. That's the one coming towards. And it's got a side that's red to you. That's the one going away. And as the planet transits, it blocks first the blue side and then the red side. Or vice versa. And it produces what is an apparent jerky Doppler shift in the star. And it's just about blocking hot side, cold side, red side, blue side. And by whether this curve goes down first or up first and then down, you can tell whether the planet entered transit on the blue side and then the red side. That would be what you'd expect if it's going in the same sense as the star. Or whether it entered the red side first and then the blue side. That's what you'd expect if it was going backwards. This planet, which is WASP 15b, is going backwards. So unlike our solar system, where everything is circling the drain in the same sense, just like you'd expect forming out of a gas disk, in this system, somehow the planet didn't get the memo. It's flipped over. It's going the wrong direction. We can make this measurement for a number of hot Jupiters, and this is what we found in 2012. The sample now is a little bit bigger, but it's basically statistically identical. Okay, some of them look like they're very aligned. That'd be like our Jupiter, always going in the orbital plane. But a number of them have orbital misalignments that are bigger than 90 degrees. So these are the retrograde hot Jupiters. And that's the final clue to their formation mechanism. Because whatever brought them in didn't do it calmly. They didn't form in a protoplanetary disk and migrate gently through the disk from gas drag and wind up inside Mercury's orbit. Okay, they had some kind of dramatic thing that flipped their orbit over and brought it. What could that dramatic thing be? Well, Dan Fabricki and Scott Tremaine wrote, let's see if I can make this play, wrote a very influential paper showed. They wrote a very influential paper arguing you could do this with a particular resonant effect called quasi-cycling. Quasi-cycling it's a secular effect, meaning it doesn't take effect on orbital timescales. It's over very, very long timescales that causes the eccentricity and inclination of the planet's orbit to oscillate. It becomes highly inclined and circular, and then not so inclined and eccentric. And back and forth and back and forth. And when it is eccentric, it's brought in close to its host star, which means tides can be raised, which means the orbit can shrink a bit. Then it goes back to circular, and then back and forth. Quasi-cycles operate whenever there is a distant object that perturbs the gravitational potential of the star-planet system. And in Fabriki and Tremain's paper, that distant object was a star, a binary companion to the planet's host. Those binary companions live at very large distances. The ratio of the distance to the planet and the distance to the star is big. And that means if you think about what the potential, the perturbing potential is from the binary companion, the only term that matters is the quadrupole term. Okay, that's the leading order term in a multipolar expansion, that's it. And it turns out that quadrupolar quasi-cycles are pretty steady. They're integrable, the quadrupolar potential is integrable, nothing terribly exciting happens, you get this kind of gentle eccentricity inclination oscillation. Well, while we were at Northwestern, Spadar and I and some other people there thought, well, what if instead of a perturbing star, you had a perturbing planet? Now you could put a planet in much closer, and if you expand the perturbing potential, you may not only care about the leading order term anymore, you might care about the octopolar term. And it turns out the octopolar term breaks one of the conserved quantities from the quadrupolar term, and could give you much more dramatic evolution. So on the right-hand side here, we're showing this is the inclination of the planet's orbit. It starts at 60 degrees, it goes through periodic inclination oscillations. The green curve here is what you get if you had a distant perturber and cared only about the quadrupole. The red curve is what you get from the octopole term added in. So you still get this cone-like quadrupolar structure, but then the octopole imposes a longer time scale, and it flips the orbit right over. Okay, the inclination crosses repeatedly 90 degrees. And at the same time that the inclination is crossing 90 degrees, the eccentricity is becoming extreme. And so if you do this right, you wind up circularizing, because of the extreme eccentricity, in a retrograde orbit fairly commonly. So we thought maybe a lot of these hot Jupiters are caused by exactly this process. There's a companion planet, it perturbs their orbit, they go through these extreme eccentricity and inclination oscillations, they flip over, circularize, and you get a retrograde hot Jupiter. Yeah?
How much does this depend on the mass of the planet?
The only dependence on the mass is in the time scale for the time scale for these oscillations. So the x-axis changes based on the mass, but in particular, the maximum eccentricity doesn't change, and the fact that you flip doesn't change. Okay, well, so we wrote a couple of papers about that. That's quite exciting, but let's confront that hypothesis with data. So here, this is angle in degrees, and this is the distribution of misalignment angles, P of lambda. Lambda is the misalignment angle. The black curve is the distribution inferred from the observations in 2012. The green curve is the distribution that we predict from our process with planets sort of scattered in the outer solar system in a reasonable way. And the red curve is from an alternative prediction where the planets are just closely packed together and they gravitationally scatter each other in a fairly dramatic way. And let's see if we can disentangle what contribution, the red curve, the green curve, and then a lazy stay disk migration that keeps everything perfectly aligned as they moved in, make to this black curve. And the technical term for this is a mixture model. We are saying that the distribution of misalignment angles is subcomponent times a delta function at 0. That's for the stuff that just gently ran in the disk. Some other fraction, we call it an eccentric quasi-Log mechanism. So some other fraction times the distribution we infer from our prediction. And a fraction times direct planet-planet dramatic scattering. Okay? So we build this mixture model and we want to infer what these fractions are. How much of each operation is happening in the overall population. And what we discovered, I'm not going to go through the whole plot, I'm actually just going to focus on this one. So this is the posterior for the fraction of the misaligned planets that are coming from our mechanism, the eccentric cosine mechanism. Now, we can't place great constraints. In principle, it could be 0. But our best fit value is that about 60% of the time when you have a misaligned hot Jupiter, it came from this mechanism. And this data set is fairly rough. We will absolutely do better than this in the near future with exoplanet observations as we measure more and more obliquities, spin orbit misalignments. So this is not like the black holes where that's about the best you can do. This is going to get much better. And I say that, the point here is not, oh yes, our mechanism wins. The point here is to illustrate you can disentangle multiple populations, and there's subpopulations. This scattering, that scattering, this drifting. There's subpopulations in the data set, you can pick them out with a mixture model. Okay? All right. Let's move onward to something that's quite exciting. Earth-like exoplanets. At some level, I guess the goal of exoplanet research is little green men. Okay? Little green women, little green people. The point, that's the thing everybody has in mind. And so, this is a first step, if you like, or not a first, a 7th, 12th, whatever step in that direction. We've still got a long ways to go. The idea here is to use Kepler, a fantastic NASA satellite that's got thousands of planet candidates, to try to infer what the distribution in period, orbital period, and radius size of the planet is. But the Kepler sample, in spite of the fact that it's awesome and it has thousands of planets in it, it suffers from confusion. Okay? There are things in the background that aren't planets that made it onto the candidate list. And it also suffers from selection. Kepler can find some planets much more easily than others. And so what you see is not what you get, if you like. Remember when we all had word processing programs that were WYSIWYG? This is whiz and wig. Okay? There are severe selection effects. So just last year, a bunch of us, this is FGMC for people in LIGO, that's the initials that we decided to name it, wrote a paper that took mixture models, that you just saw, there's this or this in the population, and it extended it to mixture counting. There's 15 of these, and 7 of those, and 23 of those. Okay? The title was Counting in Confusion. It's, for the people who really want buzzwords, it's a mixture Poisson model. And so, for example, you can count the number of foreground things and the number of background things. So you can count the number of planets that are in one near orbit and Earth-sized, and the number of contaminants you have in that region, for example. That's what we're going to do. Okay, but first an example. I don't know how many really hardcore astronomers we have in the crowd. Maybe not a ton, but maybe that's actually safer that we don't have a lot. I'm going to say astronomers like to make catalogs. Okay, usually you take a big survey, you get some objects, and then you start slicing and dicing. You cut above this magnitude, and you make a cut in color space, and maybe you make a cut in duty cycle of the instrument, So they start cutting everything down. You make catalogs first, and then you publish your catalog in AGN or whatever, and then everybody goes to town and tries to infer what is the population of AGN. If you have contamination, our argument at FGMC is don't do this. Okay? And we gave a toy example where you can't do this. So this is a synthetic field of stars, every dot's a star, and there's a globular clustering. Okay? There's 11,000 stars in this field. 1,000 of them are in the globular cluster, which you cannot see by eye. And in fact, we arranged this to be maximally pessimistic. The center of the globular cluster is right there. And at that center, the density of stars in the cluster, spatial density, is exactly equal to the density of stars in this overall background. And what that means is there's no star in this field that has a better than 50-50 chance of being in the cluster. You cannot make a catalog. Okay? Nevertheless, by writing down a mixture model, and this shouldn't be a surprise, any particle physicist in the room is going to go, well, yeah, can't you do this? I mean, if you're counting Higgs events, Okay? You don't really care which of the events in a particular region of energy, space, and undercuts corresponds to the Higgs. You care that you have an excess over your background there. That's all this is. Okay? In this region, you have an excess density, and you can count how big it is. So it's not, I mean, maybe it's not that great of insight, but it's a fun thing to do in astronomy because it's kind of neat for people going to make calculus. So this is just telling you, we counted how many stars are in the cluster, there's about 1,000, and we counted how many stars are in the field, there's 10,000. And I'm not going to show you plots, but we also inferred the cluster's properties, its typical size, its core radius, the slope, the density profile, all of these things, without exhibiting a single cluster member. Okay, that's the exciting part. All right, so let's apply this to Kepler. Kepler has strong selection biases in the parameters that it measures. Its probability of detecting a planet at a first approximation involves two factors. There's a geometric factor. Kepler is a transit mission, so the planet has to come between the star and us in order to see the planet. And that depends, the bigger the star is, the more likely that intersection is to happen. And then the further out the planet is, which is represented by this period in the denominator, the further out the planet is, the more delicate that alignment is, and so the less likely you are to see it. So there's just geometry. And then there's also a signal-to-noise ratio dependent term, where if there's more noise in the star, for whatever reason, it's harder to see the planet. And that scales like the depth of the transit, which is the area of the planet divided by the area of the star, a fraction of light that's blocked. And then scales somewhat weakly with the period, because at shorter periods you get more transits. So you can integrate for longer if you like. You got more samples in transit. Okay? So this is just an SNR dependent term. And I took some fourth-year students. In the UK, those would be master's students, Chris Aldridge and Kirsty Stroud, and decided I'd give them a project where let's fit a contaminated, just like that globular cluster example, a contaminated distribution of planets with this selection function to the Kepler data and see if we can infer everything. The amount of contamination, the distribution of the planets, the shape of this selection function, okay, all of that. And the answer was, yeah, we kind of could. So this is the Kepler Catalog, circa 2014, when they started. It's a period radius. Okay, you can see there's sort of a cluster of stars. There's not many out here at long periods and small radii. It's because they're hard to see. There's probably actually a lot of planets in this region that Kepler can't find. And what they did was they built a model, a very simple model, a log normal distribution. So in this log-log plot is a Gaussian. That's their model for the distribution of planets. Now, that's not realistic. I'm not saying that's how planets are distributed. This is a master's thesis. It's just a first cut. Okay? Then they down-selected that by the selection function. So this is what remains when you cut off the planets that would be unobservable for Kepler. And they contaminated it. All those red dots are background fits from their background model. And then they compared. So this is the real distribution on the right, and this is the synthetic distribution on the left. And they're pretty similar. And so you repeat that a bunch of times, you get an NCMC. Yep. And so this plot is intended to convince you that even though planets really aren't distributed log normally, this is not a terrible model. Okay, so in blue here are synthetic draws from that model. Okay, intrinsic population, down-selected, contaminated, plotted in blue. In black are the actual planet candidates from Kepler. And you can see that the blue tracks the black in period space and in radius space pretty darn well. There's one little hiccup here in radius where you're transitioning to gas giants. Things aren't really very smooth there in radius because the mass-radius relation has a kink in it. But, all things considered, it's not too bad. This tail here of planets that are, 60 times the size of the Earth, those are actually stars. That's contamination. So in particular, the fact that our model fits this tail suggests that we're actually doing a pretty good job of plucking out all the contamination. Okay, I'm going to skip this plot in the interest of time. So the ultimate result of all this was we could query our model and we could ask how many Earth-like planets, that's 1 year orbits, about 1 Earth radius, are there per star in the universe? And the answer was there's about 4%. Okay. So there's, 100 billion stars in the galaxy. Most of them are, typical sun-like stars. So there's 4 billion Earth-like planets in the galaxy. There's also about 4 planets per star. That's kind of a shocker because there's Kepler multiples, but there aren't that many. But you know, there's actually 4 rocky planets in our solar system, so maybe that's not a surprise, or maybe it is, I don't know. And then finally, we could infer this is the detection efficiency as a function of SNR for Kepler. This is our inference about it. And it turns out it's really not that far off the real curve. When Kepler goes and measures their detection efficiency, they get something that looks about like this. So, you know, and we didn't use any real knowledge of the instrument. We just used the fact that the distribution of planets is changing. All right, I'm going to skip. Okay, so where are we stats-wise? Well, we've seen hierarchical models in analyzing the black hole mass distribution. We've seen mixture models in disentangling hot Jupiter formation. We've seen selective and contaminated mixture models in Earths. I skipped this slide, but you would have seen hierarchical selective mixture. Okay, so we're just adding up all of the various tips and tricks and so on that I've mentioned through the talk. All right. We know what LIGO is. Gravitational waves are disturbances in space-time that come in 2 polarizations. This happens to be the plus polarization. This is what it does to your interferometer. Arm gets short, arm gets long, and vice versa. We measure that distance through a heroic effort of many thousands of people over many decades, and read out the differential distance in these arms, or rather, actually, we read out the force we have to put on the mirrors to keep the distance fixed, because that's how the interferometer operates, but same difference. What we get at the end is a measurement of the dimensionless strain, the stretching caused by gravitational waves. And the things I've been talking about in this talk, black holes, and also neutron stars, are sort of the flagship targets of LIGO. And to orient scales for you, the maximum gravitational wave frequency from an inspiraling 1.4 binary neutron star is about 1500 hertz. So a 10-10 binary black hole is 150 hertz. A 100 binary black hole is 15 hertz. This is from what we call the observing scenarios document. It's in our document repository in LIGO, and this is the phone number of it. If you just Google that in LIGO, you get there. It's a prediction. Well, at this point, some of it's, I guess, a post-prediction. But this is our strain sensitivity, so it's the noise power spectrum for root hertz. In the early times, that's now, LIGO just completed an 01 observing run. Green is mid, so that's sort of this year and next. Late, it design sensitivity for advanced LIGO. And really, I want to show you this because, here's 100 hertz, and here's 1,000 hertz. Here's the bucket. LIGO is targeting these sorts of stellar mass objects. Okay. To sort of whet your appetite, this is what we call the rates paper. It's a living review document. We try to keep it up to date. I'm not sure that it completely tracks population synthesis because that's a pretty fascinating name. But it's estimates of sources. This is an initial LIGO, which is over and done with. It's advanced LIGO. We haven't reached that sensitivity. We're somewhere between here and here. And this is predictions. This is predictions of predictions of the number of sources per year that we detect in advanced LIGO. And, somewhere between 0.4 and 1,000 EMS sources. So we've got that pinned down pretty well. The point here is that population synthesis and our measurements of these objects, I just showed you E&M measurements of the mass distribution here. There's thousands of other measurements that go into these rates, and they're all wildly uncertain. So either that's depressing, or that's an opportunity. Okay, we know nothing about the merger rates of these objects. And the instant that LIGO finds some of them, we will know vastly more than we did. Okay? No, we'll knock an order of magnitude off or something. When LIGO finds thousands of these, then we'll really have a good idea what to do. Okay? All right, Well, for each source that we find, we want to measure the parameters. And the parameters of that source that go into the gravitational wave, the masses, they control the frequency evolution, the length of the signal, the strength of the signal, are sort of the dominant parameters. Then the spin can modulate the waveform, because if the black holes have angular momentum and the orbit has angular momentum, you get precession. So the orbital plane is wobbling, and the emission is non-uniform, so you see bright and dark and bright and dark, and it does this. Okay, you're seeing here, the tiny wiggles are the orbital, twice the orbital frequency, and the slow wiggles are the spin precession modulating it. Then there's, where is the object on the sky? How far away is it? What is the inclination of the orbit? Does it face on, edge on? All of these properties of the system we try to measure for each individual system. Okay? Let's see if this movie will play. It does. The way we do that is through stochastic samplers. This is a movie showing you the evolution of such a stochastic sampler on a synthetic signal in the M1, M2 space. So the stochastic sampler wanders around trying to pick parameters that are a good match for the signal and ends up picking out a density in this 2D space that looks like this. Okay? And what I want to highlight with this is this means there's a particular combination of masses called the chirp mass that we measure really well. And it has basically no meaning except as the thing that controls the gravitational wave phase. Okay? No astronomer is interested in the chirp mass. They're interested in what is the mass. So in particular, we measure masses rather poorly compared to how well we measure the chirp mass at least. And so this is a situation where we will have to, in order to understand the population, we're just like the black holes from X-ray binaries. We don't know the masses all that well in any individual system, so to understand the population, we're going to need a hierarchical model. Okay? And it's going to have multiple components. It's going to have a binary black hole component, a neutron star black hole component, a BNS, binary neutron star component. So it's going to be a mixture hierarchical model. And there's selection effects on each one. LIGO's sensitivity to neutron stars is much lower than sensitivity to binary black holes. So it's going to be a hierarchical mixture selected model, which is everything from the early parts of this talk, actually. And in particular, we actually wrote this paper not talking about globular clusters or planets, but talking about LIGO signals. So let's suppose we're in that future that's too bright to, we're going to have to wear sunglasses, and we have many, many, many LIGO signals. Some of them are going to be exceptionally loud and clear, and you're going to just look at the data and go, aha, that's it, okay? But some of them are going to be kind of in the muck. And so the reason we wrote this paper was to do the best job of counting all of these signals that we could, properly weighing these guys that are in the muck against, what's the likelihood that they're instrumental origin, some noise trigger, whatever, versus really astrophysical. Try to get as much out of this data set as possible. I'm not going to explain this plot except to say that if I did, the method works. So we're going to have to infer parameters. We're going to have to count signals in order to understand the population. And in fact, it's recently become clear, this is a paper, I wasn't involved in this paper, but it's from the Northwestern group, Tyson Wittenberg led the paper, and Ben Farr was also on it, and it's showing a big injection campaign using synthetic signals into synthetic noise. Here's the injected mass of the lighter object. That's the one that could be a neutron star, even if the heavier one's a black hole. Here's the recovered mass, and if you look at these error bars, here is the mass gap, okay? 3 to 5 solar masses. We'd like to know if that's populated or not. And the error bars on any individual source are too big to tell. Okay? There's no smoking gun. Again, it's just to emphasize, it's gonna need population analysis in this way. You could tell if there are no sources in this region. Eventually you can tell because you just, you get an accumulation of stuff here and nothing in the middle. But you have to do it by analyzing the whole population, taking into account selection effects. Okay. Now, I'm going to end on a final slide. Suppose I talked about black holes and the mass gap, and there's one piece of physics that can tell us all about supernova, but pretend, you're like Rana yesterday. Rana was like, yeah, I don't care about black holes. Okay. So what if you don't care about black holes? I'm probably preaching to the choir, but you still should be excited about LIGO if you care about strong field tests and GR. That's another population thing. It's very unlikely that we're going to have a smoking gun GR violation. We're going to build it up over many measurements that look a little bit hinky each one. Gradually accumulate evidence. If you care about cosmology or electromagnetic follow-up, I haven't exactly played a leading role in this, but I've been in a supporting role trying to massage all of our parameter estimation into shape to support this effort to get simultaneous electromagnetic and gravitational wave observations. So you can get a redshift and a distance. Redshifts and distance, you can do an awful lot. If you care about star formation history, this plot takes the sensitivity from early LIGO, in that observing scenarios document I told you about, generates 10 plus 10 binary black hole, 20 plus 20, 50 plus 50, and 100 plus 100. Put these on the run. It's really hard to get these out of population synthesis, but he thinks they're there. So I stuck them there. And this is the distribution of these sources that we would expect in redshift if they were forming and coalescing at a constant rate in their co-moving source frame. And look at this axis, okay? So 100 black holes. Nobody thinks they really exist, but if they did, even now, LIGO could see them out to redshifts of 0.7. Wow. Okay? You're starting to really dig in, you know, star formation history. Star formation is going wild between redshift 1 and 2. Okay, this is early advanced LIGO. Just wait for the real thing. Okay, so if you care about star formation history, if you care about GRBs and supernova, well, this could be neutron star mergers. You see a bunch of those. We'll nail down the time delay distribution between formation and merger. A bunch of, you know, maybe there isn't a connection between GRBs and supernova. Maybe there is. So anyway, the point is you should be very excited about LIGO if you don't care about the black holes I talked about today. But in order to exploit all of this stuff, it's going to take this population modeling and these sort of astrostatistics that I was just explaining. And that's the end. I'm happy to take more questions.
I was wondering about so you said you measured the very equal number of 4 planets per star.
Yeah.
And I was wondering what you assumed about the mutual inclination distribution.
So we actually assume something was really stupid, which is that they're isotropically distributed. So, you know, there's not so many. You're referring to this plot. Yeah. This one here. This one here. 4 planets per star. There's not that many multiples in the data set. They're, I don't know, 10%, something like that. So it's probably not terribly sensitive to that assumption, but it is sensitive to that assumption. And we made one that's definitely wrong. Planets are not isotropically distributed. One planet passing between you and the star means there's probably others. So that's an area that a lot of people are working on, including us, to try to extend these sorts of models to figure out what that inclination correlation. Yeah.
You're talking about hot Jupiters being influenced by another planet in the same system. Have there been systems where hot Jupiters with other planets have been observed?
I think now there may actually be 1 or 2. When we were writing the paper, there were not. But there is evidence for Jupiter-like planets forming out in the 60 to 100 AU region from direct imaging. Fomalhaut is the famous one, but there's a couple others as well. And so we were trying to argue that, you know, maybe Jupiter-like things form out there, and for some reason they maybe get kicked by a close encounter, or maybe the disk is warped somehow, so they're, you know, inclined enough to start this Kozai cycling. And then everything goes. You know, that's something that direct imaging surveys will just nail. We'll just know. But at the moment, I don't think.
Okay, well, we've got, I think we have some snacks and maybe some drinks on front, so let's thank our speaker one more time and we can continue.